Right, so this will be our last video on counting principles, looking at applications of combinations and permutations. And I really hope I don't get flagged for copyright issues because I love video games. And to make this unit more fun, I used video games in my examples. So our first example of applications with combinations and permutations is Super Smash Bros. Ultimate. And you can see how long ago I made these because this 72, or excuse me, 74 is much bigger now that the DLC packs have been released. In any case, Super Smash Bros. At one time had 74 different fighters. In how many ways can 4 friends play if each chooses a different fighter? So you might be wondering, is this a combination or a permutation? Well, does order matter? Well, it kind of does, because if the first person picks Mario, for example, no one else can pick Mario. And so there's only different options. But then you could also make the argument that it doesn't matter because as long as one person picks Mario, it doesn't matter if that was the first person or the last person. The flaw with some of these examples is that it's somewhat ambiguous. For questions that end up in practice sets and on exams, it should not be ambiguous, and it'll be pretty apparent whether order matters or order doesn't matter. So, as first designed, this was intended to be order matters, in that if the first person chooses Kirby, that changes the options for all of the other players. So if we look at the number, the total is n, is 74, and then we pick R4. So we want the number of permutations of 4 objects from a selection of 74. This is a huge number. I'm going to put it into my calculator. So 74, then I use my probability menu to find NPR, and I enter 4, and it gives me, this has so many numbers in it, gives me 2, 7, 6, 1, 5, 0, 2, 4. Okay, now that I've been able to add some place values with commas, there are over 26,615,000 different ways, if order matters, that we can play, which is why the game has such great replay value, and you should totally play it if you don't already. And maybe, who knows, Nintendo will say, this guy's teaching with math with Nintendo, we're going to sponsor his videos. That would be the day. In any case, let's suppose my friends and I wanted to play a Super Smash Bros. Ultimate tournament with 16 players, each competing in one-on-one matches. How many different pairings could there be for the final match? So, in this case, a pairing would be whether it's me and my best friend John, or me and maybe my other best friend RJ. Who knows? But what we might find is that because it doesn't matter whether you're the first person in the final match or the second person in the final match, this is actually going to be a combination because order doesn't matter. So if we have 16 friends all playing together, and we want to see how many different pairs, that's 2, could be in the final, all we have to do is find the number of 16, choose 2. So using my calculator once more, 16 choose 2 is 120. So assuming that one of my friends isn't a master who just obliterates everybody. There's realistically 120 different ways that that final match could be fought. Numbers get big. Counting in math isn't just counting on 10 fingers, it's really counting to like millions and billions. It can be overwhelming, but also incredibly cool that a really small formula can give us such big numbers. Another example, carrying on with my obsession of Nintendo, is the Legend of Zelda. So Link, this guy over in green, Zelda is the princess he's trying to save. Link's gotten tired and only has enough strength left to carry 4 items. In how many ways can Link choose which 4 items to keep? So the bottles are empty, so we are going to ignore them. They will not serve him any good presently. So we have 3 by 4, so 12 different objects. So we know, I should be writing this in green. So we know that n is 12, and we know r is 4, because he only has enough strength left to carry 4 items. So, let's see, is this a permutation or a combination? Does it matter if he picks the sword and then the shield, or would it be the same thing if he picks the shield first? Oops. If he picks the shield first and then the sword. As it works out, the order doesn't matter. So we have a combination. So if I come back to my pen, we have 12, choose 4. So 12, choose 4, using my handy dandy calculator, is 495. So there's a lot of options. Maybe you really like the utility of having bombs with you. Maybe you like the ranged attack of the bow. Maybe you like being able to run really fast and sometimes roll over holes with like the winged boots. Actually, I think it's this one that allows you to jump over holes. I can't remember. In any case, in how many ways can a player assign these 4 items to the A, B, X, and Y buttons? Well, as it turns out, we have 4 items and 4 buttons, and in total, because order matters, the first item on A, the second item on B, the third item on X, the fourth item on Y, it's a permutation. So a permutation of 4 objects from a group of 4 is, for reasons we won't get into, the same as 4 factorial. So we have 4 times 3 times 2 times 1, which is 24. So there are 24 ways a player could customize their controls by assigning their objects to different buttons. To do a few examples where we are not potentially infringing upon Nintendo copyright, here's a number of examples of order mattering or not mattering. So as I go through each of these, I'm going to read it aloud, pause a few seconds, and then explain. In that time, while I have paused, you can pause the video, make a prediction, and then see. Once we determine if order matters or doesn't matter, we're pretty much done. We're going to plug it in a calculator and be all finished. So this is really where most students get tripped up, determining does order matter, why or why not. Creating a reading list of books to read in 2019 or 2020. Or even 2021. So this could be one that order matters or not. You could say that you are making a list to read in order, but if your reading list is like just a bunch of books, order doesn't matter, you might put it here. However, because it's a list, I'm going to assume that order matters. Choosing classes for your first semester of college. Order might matter because, if you pick a class at 9 a.m., you can't pick another class at 9 a.m. unless you have a time turner, at which point I'm envious. Selecting friends to invite to a party or other event. Hopefully, order doesn't matter because all of our guests will be equal. They're all guests. Electing multiple leadership positions in an organization. Typically, when we're electing positions, order matters. For example, we have a president, then vice president, then secretary and treasurer, or treasurer and secretary. And so the order matters. The qualifying rounds of a sports competition. Order doesn't matter because as long as you pass the first round, you move on to the next one. A contest in which prizes are the same. Order doesn't matter. If first and second place get the same thing, it doesn't matter who's picked first or second, they get the same thing. Creating a seating chart. Order matters. A contest in which the prizes are different. This is another case where order matters because your first person and your last person that you pick will end up with different things. Lastly, forming a committee. So on a committee, which is another form of leadership, everyone has the same responsibility. They are all equals, unlike multiple leadership positions. So forming a committee. The following slides, which will be included in the notes that I upload to Google Classroom, include 5 practice examples with explained, worked out solutions, highly color-coded as well. And lastly, including the graded homework for this lesson. So these are just 3 questions that you'll need to answer individually for a grade. And that brings this first lesson of Module B to its end.